This worksheet involves free body diagrams. Now remember that free body diagrams are basically a convenient way of representing all of the forces on a single object. Okay. The first problem asks, a cat sits on a physics book sitting at rest on a student's desk. Draw the free body diagram for the book. Okay, so the first thing that we should do is draw a picture of this situation. Alright, so we'll first draw a picture. Okay, so maybe we have a desk, and we have a book sitting on the desk, and we have a cat. Sitting on the book. Okay, so the book is the object that we're interested in. So the next step is maybe to identify all of the forces on the book. And remember, we just need the forces on the book itself. So gravity is the easy one. Gravity is in any problem that's based on Earth. Okay, and maybe we'll give it a variable name. We'll call it maybe W sub B for weight of the book. We also have the force of this cat, so I'll just say cat, which we recognize immediately. This is going to be the weight of the cat. So W sub C, and we also have a normal force, right? The other object that the book is interacting with is this desk. So call it maybe F sub N. Okay. So now I'll draw the free body diagram. I'm going to label this F, B, D. And I first need to set up some axes, right? So the orientation of these should be pretty simply straight up and down, straight right and left. We'll label this X and Y. And remember, the object of interest is the origin. Okay, in this case it's the book. So now I can draw these three forces, the gravity acting on the book, the cat pushing down on the book, and the normal force pushing back up. Maybe I'll start with the weight of the book. So I'm going to draw this just a little off to the side of the axis so we can actually see it. Okay, and we'll label it as W sub B. Now we need the weight of the cat, which is also, it's pushing down, but again we start from the axis, from the origin. Let's say the cat's maybe a little heavier. We're not given this detail, so we could modify it for some specific problem. And now I need the normal force. And the normal force points up, and it actually should be the length of both of these arrows put together. Right? Since we're assuming the book is not moving up or down, it's not accelerating up or down, the net force is 0. Okay, so here's the normal force. And that's roughly the size of the sum of these two things. And this is our free body diagram. Okay. So looking at the second problem, a block is pulled up a hill at a constant rate by a rope that is parallel to the incline. Draw the free body diagram for the block. Assume you cannot ignore friction. So again, we will draw the picture. So here's this. We weren't given an angle, but let's label an angle. And we're pulled up the incline, parallel to the incline. Okay, so 2 is identify the forces. So again, gravity's the easy one. And we'll give it a variable name immediately just so that we know what we're talking about. If this is being pulled by some rope, there must be some tension. Maybe just call that T. If it's sitting on an incline, there must be some normal force. And we're told that we cannot ignore friction, so we should put friction here as well. Okay, now that we have our list of forces, we can draw our free body diagram. So the axes for these, it makes sense to tilt this. Okay, we don't have to, but it's strongly suggested by the setup of the problem, right? So let's draw this nice and big. Maybe here and here. And our object sits at the origin. So maybe the first force that makes sense to put in here is weight, or gravity, and that points straight down, and straight down looks like this. Let's label that as weight. And we should identify where this angle is, right? What angle is this to maybe the y-axis or the x-axis? And one convenient way to think about this is if this incline got shallower and shallower down to theta equals 0, which angle here becomes 0? Well, the weight continues to point straight down, but the x-axis would rotate until it pointed directly to the right. And if x pointed to the right, this angle would be 0, so this must be theta. Alright? And before we go much further, let's just break weight into x and y components. Okay, so we're not adding a new force, we're just imagining what are the bits that make up the weight, right? What is the x bits and the y bits? So the y bit looks like this. We'll label it as w sub y. And the x bit looks like this. There's w sub x. Okay. So now we can go to tension. And let's say that tension looks like this. Okay, to a certain extent we would have to have some numbers given to us from a problem. Although we can immediately say, because this is going up the incline, this tension has to at least match the x component of weight. Right? If the tension were smaller than the x component of the weight, this would actually be falling down the incline, slowly, but it would be going down. So tension has to be at least equal to the weight. Since we're thinking about the x-axis, let's do friction now. We're told that this is traveling at a constant rate, right? Meaning constant velocity, and a constant velocity means zero acceleration. Okay? Zero acceleration means that the net force is also 0, right? In both the x and y directions. The y direction is pretty obvious, but in the x direction, that tells us that tension plus the x direction of weight plus the only remaining x direction force, which is friction, must add to 0. Alright, and that tells us how big friction should be. Alright, so the weight is this long, and the difference between that length and the tension's length is about that big, so I can draw that right here. And that looks pretty reasonable. Alright, so now you can see that tension equals friction plus weight. Right? And finally we can put in this normal force, and the normal force should exactly equal the y component of weight in this case. So we'll draw that here. So in. And there you have it. This is our free body diagram. Okay. Strictly speaking, the Wx and the Wy don't have to be part of this, but they're useful to include because you're going to need that when we fill in the Newton's second law using this diagram.